given in arrays. So generally, when array is given in this form, then we call this, if this is A, then we call this A1 and then A2. But sometimes you can use little endian, so this can be A1 and A2 and so on. And then B can be given in this form. Then we can multiply A and B to create C. And then C may look like this. So this is the task. And to do these things, we must know about basic mathematical theory, but that theory is very trivial in some sense. So assume that we multiply 1, 2, 3, 4, 5, 6, 7, 8, 9 by 1, 1, 1, 2, 2, 2, 3, 3, 4. Then A is this one, B is this one. Then C should be created, and then initially we fill 6 boxes with zeros. We fill 6 boxes with zeros. And then each time when you have any result, we add the result, right? So for instance, if we multiply these two, then it will become a 6-digit number, right? It will become a 6-digit number. So 3-digit here, 3-digit here should be stored with this addition to 0, 0. And then if we multiply these two things, then we should add the result to these two places. So essentially, what you do is these things, right? What you do is these things, and I will show you one example. I grabbed some results that some of you submitted. So A times B. Then as you can see, this is the result. A is given in array, right? A is given in array of 3-digit numbers, right? Array of 3-digit numbers. And then B is given in an array of 3-digit numbers. And then A times B is calculated, right? And then it's given in this format. Without this program, if you want to multiply big numbers, you must rely on MATLAB built-in functions. MATLAB built-in function cannot handle these kind of things. Some of you may ask me why these are necessary. These are very essential in cryptography. When you code information, you send your message. First, you scramble this message like this using numbers, right? For instance, help me, or attack some place, and then you use numbers to encode the message. Afterwards, you need to do this kind of operation, and then eventually you send this kind of result. Then even if someone intercepts the message, they don't know what the message is because it's scrambled. Unless they know, for instance, key like this B, they don't know. So once the message arrives, they can divide this by this kind of number to retrieve the given message. So it's very essential in cryptography. But unfortunately, MATLAB does not support this kind of big number calculation. Does any of you find any MATLAB built-in function doing this? As far as I know, several people tried to find, but they all failed to find this kind of function in MATLAB. Maple already has built-in function like this, but MATLAB doesn't. In any case, this is what I want. So I will pause and then you can check what is going on. In other words, this program is very robust. No matter how large the number is or how large the array is, it can handle completely. and then you can generate A times B. So I will show you this kind of result. So you may ask, of course, you don't have to create this kind of nice result. If you have 0, 2, 2, in your result you can have just 2, 2. Then it means 0, 2, 2. Because it's like a placeholder. So for instance, if it has 0, 0, 2, then you don't have to add any more routine doing this conversion. The person who coded this also considered this thing and then added this portion, but it's not required. It's nice to have this, but it's not required. But at least, as you can see, if you have 0, 0, 0, then just you can write 0. So I will pause and then you can browse and check whether you completely understand the problem or not, because already about 7 students submit homework, and there are only a few who didn't finish these things. But if you still have questions about this program, ask me. I chose this because it doesn't involve high-level mathematical theory at all, right? Only basic mathematics that you already know. But program-wise, it's no easier, right? This is no easier than hard PD problems. This problem and hard PD problems are solved by the same programming skill. So, no questions? So input is given in this pattern. So A times B, these are input arrays. Then from these two input arrays, we get the result array C. So I will re-mention about the strategy of doing this one more time. Initially, to hold A, you need an array, right? So this is array 1. And then to hold the second input, you need array 2. And then you need to hold the result in C. So as far as memories are concerned or storage places are concerned, you don't have to have more than these 3 storage area, right? More than 3. You don't need more than these 3. And then the only thing that you need to do is determining the correct position to fill, right? If we multiply these two, we fill these 2 arrays, these 2 boxes, right? If you multiply these 2, you should fill these 2 boxes. And then if addition of this goes to the next digit, right? It has more than 3 digits, then you consider the carryover, and then carryover should be added to this portion. Stuff like that. So I will pause, and then you can ask questions. If you don't, then I will begin to cover the floating number conversion, real number conversion to bits. Any questions? Yes?
Is it necessary to initialize C with all zeros?
Because it's easier to just add to appropriate location. In other words, assume that you have the multiplication of these 2 numbers, then these 2 numbers will occupy these 2 boxes. So instead of just writing the result here and then overriding anything underneath, just adding might be better, because in the future some more numbers may fill this position. Then what would you do? It's better to add to the previous result than just overriding or doing something else, right? Just adding and adding, keep adding stuffs. So in other words, these 2 things are added here, these 2 things are added here, these 2 things are added here, and so on, and then all added together. And then once there is an overflow, I mean 4-digit number appears, then you cut the carryover portion and move it to the next, and then essentially you fill these things with 3-digit numbers. And once you have 0, something, something, then you don't have to attach 0. It's not required for the exam. I mean for the homework, but it may be necessary for you to use in the future. Assume that you need to multiply big numbers to do cryptography or something, then it's good to have that kind of routine. Any other questions? Then I will briefly review one more thing. Review one thing that will be used today. I mentioned about many things, and this thing will be used today. any number with any base, right? Base 1 can be converted to the number with any given base, right? B2. It's possible to convert any number, any integers or any real numbers you can convert. For instance, I chose this number, 3.75. Then we can convert this thing with base 10, right? With base 10, I can convert this thing to the number with any base. So let's pick base 2. Then, as we did before, in this set, in this representation, we can use total 10 numbers from 0 to 9. Right? From 0 to 9. So we use numbers such as 3, 7, and 5. But in this case, we have only 2 numbers available, right? Such as 0 and 1. So using 0 and 1, you should represent. So the idea is this. 3 is 2 plus 1, right? 3 is 2 plus 1. That means 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 plus 2 to the power of negative 1, 2 to the power of negative 2 with appropriate coefficient, right? So let's determine the coefficient. 2 to the power of negative 1, that means 1/2. With 1/2, we have 1/2. So 1 is here. And then 0.25 is here. Then 1 times this one. So because of this reason, we can write it this way. In other words, any number can be written in terms of a number with base 2, right? So I covered this since last time. And if you have any question about this, ask me. If you don't, then I will use these things to convert floating numbers to bits, or bits to floating numbers. So I will pause, and then you may ask questions, and then I will use the IEEE standard for the real number conversion. No questions? Then this is the situation. Assume that people decide to follow these things and then create bits. Then they might create bits like this. 3.75 with base 10 equals 1, 1, 1, 1 with base 2, right? Then, this is my design. It's not IEEE, right? My design of bits, right? So assume that I decide to design, then 1. So 1 means on, right? On. And 1 means on, and then point is here. So point, so how can I represent point? It's difficult, right? How can I represent point? And do you have a nice idea to represent points using bits? What would you do if you want to? So yeah, we may specify the position. In other words, point is difficult to represent using bits. In other words, assume that I decide to use I decide to use 3 consecutive empty boxes to represent point. Assume that I design this way. Assume that the number itself has these things. Then how can you differentiate the empty boxes or number representing this portion? It's impossible. So point is difficult to decide. So instead of following this direction, instead of trying to convert these things to bits, we just fix the number. We fix the position, right? We fix the position. Assume that I have 10 bits available. 10 bits available. Then first 5 bits represent the numbers before the decimal, before this point, right? Before this floating point, and then 5 points after. Then in this sense, what can you do? oh, we have 10 bits, right? So this is the point, right? This is the point. Then, how can you represent? Oh, 1 is here, and then 1 is here, and then 1 is here, then 1 is here, and then zeros, right? So it is like this: 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. If we decide to follow my design, what is the problem with this direction? Assume that we want to represent 100. 100. Then we must use all the bits that it cannot represent these things with bits. In other words, my number system with this design is very limited. Any number, any big number like such, any big number such as 100 will create overflow, right? Will create an overflow. Do you follow me? So this design is not great. Because of this reason, IEEE does not follow this design. Straightforward conversion is not followed. No matter where you fix this floating point, it cannot cure the matter, right? It cannot cure the matter. Assume that you have like 64-bit numbers, and then you decide to use just one number after this point, right? Then means you can use 63 bits to represent the number, and then 1 bit to represent any fraction part. So assume that you design this way. Then what is the maximum number that you can represent with this design? Maximum number with this design is what? 2 to the power of 63. It's not very big. 2 to the power of 63 is not very big. It's big, but not that big, as you will see. It's not that big, right? Especially as you saw in coding or cryptography, as you can see, we may need to have the big numbers, right? So it's not that big. In addition, accuracy is terrible. Accuracy, because we only allow 1 digit after this point. How can you represent, for instance, 1/3 or 1/4 or 1/8, right? All these numbers have only one place to occupy, right? Either 0.0 or 0.5 in decimal representation, right? Do you follow me? If we allow just one number after this point, then our precision will be very bad. Because with 1 digit afterwards, what you can represent is 0 or 0.5, right? So any number in between cannot be represented. Either it should be this one or this one, right? Or this one or 1, right? The next one. So it's terrible if we follow this. Then to increase the accuracy, we should move this floating point to the left, right? So assume that, about 10 points are enough. Then 10 points can be used, and then 54 points can be used for the number. Then let's do the calculation. Then it decreases, right? 2 to the power of 54. Then the maximum number that we can represent decreases. So as you can see, this design is not very robust. So initially, if you somehow find old circuit board or some chips, then you may find some bad designs before IEEE standard. Any questions? Then today I will mention about IEEE standard. So my design is not very promising or robust because it has flaws. If we, of course, to cure this problem, we may increase the number of bits. In other words, instead of using 64 bits, let's use 1,000 bits. But then the performance will be very bad, right? It may be very slow. In addition, we waste too much bit space. So in any case, this direction is not very good. One thing that I want to check before I go any further is this one. Assume that we have 10 bits. Then what is the maximum number that we can represent with these 10 bits? What is the maximum number of numbers that we can represent? 2 to the power of 10, right? On and off, on and off, on and off, right? 2 to the power of 10 is the maximum. In other words, assume that we have 64-bit real number or integers or something. The maximum number that we can represent, maximum number of numbers, right? Maximum number of numbers that we can represent is limited to 2 to the power of 64. Then this means we are using smoke and mirror to represent actual numbers, because real number between 0 and 1 are infinitely many. There are infinitely many numbers. But all numbers that we can represent is limited by this number. So some numbers we may not be able to represent at all, even if we follow any design scheme. IEEE scheme or my scheme, it cannot represent some numbers. In other words, assume that some computer or some chip maker decide to follow my design with 63-digit plus 1-digit scheme. Then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, like I will use 10 numbers. So if I represent these using bits, then 0 is filling the 63 digits, right? And then 1 digit can be represented, right? By either 0 or 1. 0.1 is close to 0, right? Either 0 or 1/2 is close to 0, so I should fill this with 0. What about this number? The same thing, right? The same thing. What about this number? Still the same. 3 is closer to 1/2, so 1. 4 is close to 1/2. 5 is close to 1/2, so all zeros here. And then 6 is close to 1/2. 7 is close to 1/2. And then this number is close to the next number, right? 1, 0. So as you can see, even if these are all different, right? Or even if these numbers are all different, if we follow this design, then in computer, all these numbers are represented by the same representation, big representation. This is the source of a lot of errors when you run programs. When you run programs, your program may have this kind of problem. No matter what design you follow, the number of numbers that you can represent by bits are limited to the limited by this number, right? 2 to the power of something, right? Assume that you use n bits, then 2 to the power of n is the maximum number that you can represent. If we have overlapping thing, then it may represent smaller than these numbers, right? So I want to mention this thing before we go any further, or before we cover technical steps. But if you have any questions up to this point, ask. Yes?
Back to that array that you had up there for a second. You got down to 0.6. Why didn't it increment?
0.6 is still close to 1/2, not 1. So between 1/2 and 1, what would you choose?
Okay.
So still, I am using round off. But if you decide to use truncation, then anything under 5 can be truncated. And then anything under 1 is truncated. But if you want to round off, then you should find the closest point. If we have a tie, we usually use the right-hand side number, right? Bigger number. So, in some sense, no matter what design you use, real number use smoke and mirror. In other words, as bits show some number, but it doesn't cover all the numbers. So I will use IEEE type design. IEEE is limited to two cases, 32-bit and 64-bit. But I will use IEEE type number, such as how many digit number under 10 do you like? How many bits do you like under 10? I will design that kind of number. You may choose how many numbers you want to represent using number of bits. 8. So 8-bit is chosen. Then take a look. We should take care of two things. One thing is sign, plus or minus, right? So to represent sign, 1 bit may be necessary, right? 1 bit may be necessary. So 1 bit is gone. That means 7 bits are available. Then, if it follows my design, then the number of numbers that we can represent is limited to this number, right? If this follows my design, then 2 to the power of 7. What is 2 to the power of 7? 150? Thank you. Sorry, 128. Right? So all the numbers that you can represent these many numbers. So this direction is doomed. So what I want to do is this one. Oh, let's represent the number this way. Assume that you have 11.11 in binary representation. Then let's rewrite it this way. Oh, 1.111 multiplied by base, right? Base is 2, right? So I will use base. Base means 2. 2 to the power of 1. Do you follow me? So I want to convert the number in this pattern and then store some information of this thing in this bits. So if we break up this way, then we can use some portion to represent exponent, some portion to represent these kind of things, right? So we should determine how many numbers, how many bits we can use to represent the exponent, and how many bits to represent this portion called mantissa. But I will mention about these things later, but roughly two things should be represented. This power portion and then this portion, but we have only 7 bits remaining. So it's your design decision. How many bits do you want to use to represent exponent? It's your design decision.
Well, we need at least 2 because we need to assign one for that one as well, right?
Yes and no. I will let you know the reason, but yeah, at least 2. So maybe 3 might be fair enough, right? Or 4, and then 4 and 3, or something like this, right? If we reduce this too much, then we can not have good precision. If we have too small or too big, then we cannot represent a lot of exponents. So 3 exponents, this can be used, and 4 can be used. Then, in design time, every bit is very precious. Because of this reason, sometimes people just use this thing for convenience, but sometimes this wastes 1 bit. Why? When you have 0, then plus 0 and minus 0 share the same, use 2 different spaces, right? So, in exponent representation, even that kind of 1 bit is too much. So I will let you know the design. But you pointed out. Then what about the initial thing? If we do not waste this thing, then it's too tough to represent negative numbers. So we waste that kind of thing in the first design. but in the exponent we don't want to waste. So in this sense, the maximum number that we can represent using IEEE design is in fact this many numbers, right? Because 0, plus 0, and minus 0 have a different pattern, even though they are the same numbers, right? Plus 0 and minus 0 are the same, but because of the design, plus minus, it wastes one space, but 1 is nothing compared to these many numbers. But in the exponent, even 1 bit waste is too much. So I will let you know how they designed this. But before going any further or technical, if you have any question, ask me. We are designing and then understanding the idea.
Show me how you got that equation there if you have a base
2.
Base 2. Yeah.
Right.
How does 11.11 equal?
Oh, I see. I will explain it. So let's go back. Let's go back to that portion. So this is the situation. When you have 1, 1, 1, 1 with base 2, this means 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 plus 1 times 2 to the power of negative 1 plus 1 times 2 to the power of negative 2. But if we extract 2 to the power of 1, then what happens? If we extract 2 to the power of 1, what happens? Then it happens this way. So mathematically, 1 times, right? This is times. So in binary representation, this means Any other questions? Then, if you don't have a question, then let's handle the exponent portion. So how many bits are there to represent the exponent? 3 bits, right? We decided to use 3 bits. Then, for instance, this bit using numbers, so off, right, 0, 0, 0, should represent some number, right? And the maximum number that you can represent is 1, 1, 1, should represent something, right? But people decide to keep these precious 2 numbers. All bits are off, right? All bits are off, or all bits are on. It's very special, right? All bits are off or all bits are on. These are very special. So people decide to use these numbers for special purpose, and this is used for infinity representation or not a number representation. That means this is off the table, and the maximum number that we can use is this one. Do you follow me or not? We have 3 bits that we can use to represent an exponent, and 0, 0, 0, all off or all on is very precious, so we want to use these things for other purpose than just representing a number. So when all exponent bits are on, then we call it an infinity or not a number, and I will let you know how to distinguish these things.
Infinity or not a number?
Not a number, right. So sometimes it becomes infinity, sometimes it becomes not a number, and I will let you know how to do it. And then these are zeros. Also it's precious too. Because it's precious, we want to use this thing to represent some case called the denormalized case. 0, 0 is off the table. That means minimal exponent that we can use is 0, 0, 1 bit, right? It's not a number, just bit representation, right? Bit representation, maximum bit representation to represent a number is 1, 1, 0. Minimum representation that we can represent the number is 0, 0, 1. So let's locate these things. So minimum number is 0, 0, 1. And the maximum number is 1, 1, 0, and in between, right? So 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, and then 1, 1, 0. And then 1, 1, 1 is infinity or not a number. 0, 0, 0 is the normalized case. So all numbers that we can use is in fact 6 to represent the exponent. But we need to represent both positive power and negative power, right? Positive and negative power. We have only 6 numbers. So what should we do? Oh, I want to represent 0, zero's power using this number, and then first power using this number, and then second power using this number, and then third power using this number, and then negative first power using this number, and then negative second power using this number. So this is the design. This is the actual triplet design. Of course I used 8 bits, but whether 32 bit or 64 bits I used, this is the design. Then you may wonder why people chose bigger number here than this one. The reason is this. This case can cover something under this number too, right? This will cover something under this number. That will be mentioned later. Because of this reason, in some sense, it's not very unfair, right? Negative 2 is represented here. 3 is represented here. So it looks unfair, but it's not unfair. Because of this half. In some sense, we could go a little bit higher than this one. We could represent 4 and so on. So it's just the design decision. Then, how can you decide this kind of point? How can you decide this kind of zeroth power position? And we call this kind of number bias. How can you decide this kind of bias? And it's very simple. Assume that n bits are used to represent the exponent. Bias is nothing but 2 to the power of n minus 1 minus 1. This is the bias. 2 to the power of n minus 1 minus 1. So 2 to the power of 3 minus 1. That is 2 to the power of 2 minus 1. So 3 is the bias, right? 3 is the bias. So bias is defined by 2 to the power of n minus 1 minus 1. And n is the number of bits for the exponent part. So assume that you decide to design differently. Assume that you decide to design, I will pause and then go. Assume that you decide to design differently. In other words, instead of using 3 bits to represent exponent, if you decide to use 6 digits, right? 6 bits to represent an exponent, then what is the bias? Bias is what? 2 to the power of 6 minus 1 minus 1. 2 to the power of 5 minus 1. 32 minus 1. 31, right? Or in bit representation, 1, 1, 1, 1, 1, 0, right? So in bit representation it's easier, right? 0, 1, 1, 1, 1 is 0's power, in fact. If bit representation is this, then power is 0. If you have bit representation like this, then something multiplied by 2 to the power of 0 if bit representation is this. So I'll pause, and then you can check whether you completely follow everything up to this point. If you completely follow everything up to this point, then I will cover the last portion, fraction part, or something called mantissa. No questions? Then, finally, we can represent 4 bits, right? 4 bits to represent fractions.
Can you stop it for just a second?
Mm-hmm.
The 6-bit number that you wrote up there, 0, 1, 5 ones, that number is not 0, right?
What do you mean number? Exponent? You mean exponent?
Yeah, you've got it pointing to that 0 there, but I'm not sure I understand what that 0.
I see.
What does it represent?
So assume that. So assume that this is the sign bit, and 6 bits for exponent, right? 6, and then you see this kind of thing. And then fraction part will come here, right? Something fraction part, right? Some fraction part. So sign is something, right? So sign could be, for instance, 1, and then exponent could be this, right? And the fraction could be this. Then this portion comes here, and then this portion is sign, and then this portion represents 0th part. Any questions? Then finally, I want to represent this fraction part. It's not straightforward conversion like this, so it is a little bit misleading. So I will replace these things with different letters. Instead of x, I will say y. It's not straightforward conversion. So we have 4 remaining bits. We have 4 remaining bits to represent fraction part, or something called mantissa. Then this is the design. Assume that you have 1.000111, something like this. 2 to the power of anything, right? Something like this. Then, as you can see, it's possible to use on, off, on, right? It's possible to use this way. But we want to represent everything in standard notation, right? Standard notation, and standard notation means this. We always begin with 1. We always begin with 1 point something. Always begin with 1, multiply by 2 to the power of. So let's call this standard notation. So if we decide to follow this standard notation, then the starting number before this point is always 1. In other words, we don't even have to store this number anymore once it's written in standard form. Right? In other words, we don't have to store this information at all. We don't have to, because it's always 1. So we skip this number in our bit representation, and then we just represent these bits. This is it. So we always skip this number and store just these things, because once a number is written in this standard form, binary standard form, always we begin with 1 point something. So 1 point can be removed.
When you said that we had 4 bits remaining, were we?
Oh, we are not. We are not. I'm not covering this 4 bits yet. I'm just mentioning about standard form representation. Assume that we have many bits, and we are standard form, and then this is the case. In other words, assume that we have 1.101010, and then we have 6 bits to represent fractions. Then what should we do? We should represent this thing using, this is the fraction part, 1, 0, 1, 0, 1, 0. This is it. Right? This means 1 point distance. So I completely explained individual part. So assume that we want to represent this number using 4 bits, then what is it? 1, 0, 1. If it is truncation, 0. If it is round off, then 1, right? If it's truncation, it is 0, right? Truncation, we don't care about anything following it. But if it's not truncation, then we can round off. So I completely explained the individual parts, and now let's do some exercise. So I will pause and then wait, and then you may check individual part. Sign is too trivial, right? On, minus, off, plus. On, off. Sign bit is trivial. Exponent bit isn't difficult, right? We find the bias. Bias position is 0th power, and anything added there is plus power. Anything subtracted here, there should be negative power. Bias isn't difficult. And finally, fraction bits can be written in this way, and we call this normalized number. This normalized number, because we skip this number in the representation. Then I will ask you to convert bits to numbers. So what does this mean? So sign bit, exponent bits, fraction bits. So please find this number in decimal form. Of course, first find it in binary form and then convert it to decimal form. What is this number? If you didn't get this result, please let me know. So I will begin to explain. It is 101. Bias 0, 1, 1, right? So we subtract 0, 1, 1. Or we count it 0, 1, 1, and then the next number 1, 0, 0, and next number is 1, 0, 1. So it is 2, right? Offset is 2. And then 1, 1 represent this thing, 1, 1, and then missing, skipping number 1. So total 3 ones, right? We have 2 ones here, and skip to 1, 1. So 1, 1, 1, this one, and then 7, 4. So eventually 1.75, so 7 is represented this way. So I will pause and then you can ask questions. If you don't understand, ask me. Yes?
Sorry, I don't understand that at all. Kind of just
What part? What exponent, fraction, sign, what part?
How about the sign? We have 0 for a plus. Is that the sign of the exponent or the
No,
sign?
that's just the sign.
Sign of the number.
Sign of the
Yeah,
number.
plus 7 or minus 7, sign of the number, whole number.
How did you get the 1100 to be 1.11?
So it is normalized one, and as I mentioned, what should we do to store this thing in bits? Once we have 1 point something, we don't store this at all, and then we store these things in bits. So we have 1, 1 here, 1, 1 stored here. So 1, 1, 0, 0 stored here after skipping this bit. So you mentioned about the stubs. So take a look. We have designed 8-bit number, and 1 bit will be used for sign, 3 bits will be used for exponent, 4 bits will be used for fraction. Any questions about this? 1 bit for sign of the number, plus or minus 7, right? 3 bits will be used for exponent like this, right? Exponent like this. And 4 bits will be used for fraction part like this. So any questions about this rule? Yes?
The 1 plus 1 times 2 to the minus 1.
Yeah?
1 times 2 to the minus 3.
2. It is 2.
Where I was gonna say 0 to the 1 times 2 to the 4, 1 plus 1 times 2 to the 3 plus 0 times.
Oh, that is after the floating point. That is after this floating point. After this
Right.
is represented there. In other words, assume that you have this kind of number in general. What is this? This means what? 1 times 2 to the power what?
Minus 1.
And then?
1 times 2 to the minus 2.
Right. That's it. In general.
Okay, so you didn't write the zeros in, that's all. In that previous example, up there.
As I mentioned, when you use this scheme, we don't write anything before this floating
I
point.
mean, in your example,
Yes.
go back to your
Yeah,
example.
yeah.
Okay. Those the last 2 zeros, you just didn't write those in.
Oh, I see. That's right. That's right. Because it's 0 times something, 0 times
Okay,
something.
you
Yes,
just
yeah,
didn't write it.
yeah.
Okay.
If you want, you can write it, but it's 0. So please.
Screen back.
Any questions? Yes.
So related to our homework, when we're converting things to bits,
Right.
how many? Do we just need to tell you how many bits we're leaving for this for the?
Oh, I see. I will return back to that, and then I'll let you know the standard.
Okay.
Yeah. So 8-bit real number is explained, and we will do plenty of exercise problems. So you may pick any bit representation. 8 bits can be written anyway, so you may pick any number. So what do you want? Plus, 1 or 0? 1 or 0?
1.
And then? 1 and then?
1.
And then?
1.
We
One.
need a 0 in there.
Yeah, because we don't want have infinity case, right?
So what happens when it is infinity though?
Just infinity.
That's
Yeah,
when MATLAB
yeah.
takes out all the null.
And then what number would you like here? What bits would you like here?
1, 1, 1, 0.
That's it. So let's check what this number is, right? Let's check what this number is. So,
Same way.
yeah, please try this thing on your own, but it's good to interpret this kind of number? Any questions? This is the binary representation of the number. Of course, I will convert it to a decimal representation later. But if you have a question up to this point, ask me.
Is there just a really quick way to go from whatever our bias is to what number there is? Because I'm having to write them out and count.
Oh,
I
I
just
see.
see how to do the addition.
Roughly, you remove the beginning bit. You remove the beginning bit, and then add one,
Remove the beginning bit.
and then add one.
All right. Thank you.
So I will pause, and then you can ask questions about this conversion of those numbers, right? Sign bit is 1, that means negative, right? Exponent bit is 110, right? 110 means representing 3. And fraction is 1110, because we skipped 1. 1 point this thing, right? These 4 things are represented after skipping this number. So it should be this one. So this is the number that we want to represent in binary representation. Any questions? Then let's convert these things to a decimal number. Then minus 1 times 2 to the power of 0 times 1. 1 times 2 to the power of negative 1. 1 times 2 to the power of negative 2. 1 times 2 to the power of negative 3. And then 2 to the power of 3. Because of this reason, it is 15. Negative 15. So I represent negative 15 using bits. So you randomly chose a number, and I converted it. So I will go to the next page, unless you have questions. If you still have a question, ask me. Always decompose the bits into rows, right? Into individual rows, and then you interpret individual bits to appropriate things. First bit represents sign. Second group represent exponent with bias, right? Exponent with bias. Fraction represent normalized number. Skip after skipping, beginning, starting 1 point something, right? 1 point skipped.
If we had had all zeros in the exponent?
In the fraction?
Yes. Or the exponent. Make the exponent.
Oh, that kind of case will be covered later.
Denormalized.
Yeah, denormalized or infinity case will be handled later. After completely understanding everything other than special case, all of our own case on the exponent. Any questions? Then let's redesign. Instead of designing this way, I want to design different way. Oh, what about using 1 bit for sign, right? Because we don't need more than 1 bit to represent sign. And then instead of using 3 bits, I will use 4 bits, right? 4 bits. I will use 4 bits to represent exponent, and then 3 bits to represent fraction. So I change the design. Then what does this mean? So please find the number represented by these bits. Because there are not many numbers. 1, 0, 1, 1, 1 is the zeroth power, right? 0, 1, 1, 1 is the zeroth power. 0, 1, 1, 1 is the zeroth power. Then what is the difference between 1, 1, 1? Only this middle number. This middle number represents 2. Did you get this result or not?
Negative.
Thank you. So did you get this result or not? If you didn't, then I want to know what is the difficult part. Yes.
Remember how you wrote the exponent chart for the last one in binary?
Yes.
Do you mind writing it for this one?
Oh, no problem. If you have enough time, of course, computer will do it, but if you have enough time, you can do it. So, 0, 1, 1, 1 represent the bias, right? 0. This is the bias, right? So bias is always 1, 0, 0, 0, minus 1, right? So this is the bias. Then we can go up or down. If we go down, we should subtract 1, right? If we go down, if we subtract, if we go down, subtract, and so, right? If we go up, then this is always 1, right? 1, 0, 0 is always 1. So in this, we get negative 1, negative 2, negative 3, and we can represent more numbers after this. So this is the exponent chart. Always bias is 0, and then 1 fills all the remaining positions. In this sense, 1, 0, 0 is 1. So if you subtract 1, 0, 0, 0, then you are subtracting in real exponent 1, right? If you subtract 1, 0, 0 in bits, it means you are subtracting 1 in exponent. So exponent part is completely explained, and normalized part is also not very difficult. And final example, if all of you find this result, then I will cover the next thing. So 8-bit number with the same design. Then take a look. So what is this number? Did you get this result or not? If you didn't, then ask me or check your answer. No questions? Then, using this system, question? Using this system, let's represent the biggest number and the smallest number. So biggest number could be magnitude without considering sign. Then so without considering sign, exponent, biggest exponent is this one. And then biggest fraction is this one. Can it be any bigger than these or not? It cannot be any bigger than these things, right? It cannot be any bigger than these things. Then this number means 7. After removing this thing, add 1, right? Then 111 is 7. And fraction is 1.111 with binary representation. So biggest number that we can represent is this one. Absolute value 1.111 111 with binary representation multiplied 2 to the power of 7. Then this number can be rewritten 2 to the power of 0 plus 2 to the power of 1 times 2 to the power of negative 1 plus 1 times 2 to the power of negative 2, 1 times 2 to the power of negative 3, and then 2 to the power of 7. Then we multiply 2 to the power of 3 inside, then 2 to the power of 4 is remaining, 2 to the power of 3 is multiplied, then 1 plus 2 plus 4 plus 8. So total is 15 multiplied by 16. So the maximum number that we can represent using this is 240. So if you have a question, ask me. If you don't, then I will calculate the smallest. I will calculate smallest number later, because maximum is calculated, smallest number will become covered later. Other than 0, of course. Other than 0. So using this system, what is the smallest number that we can represent? But this is not the smallest number that we can represent for the whole cases. Only for this case, the smallest possible number is this. Exponent could be 0,001. Fraction could be 0,0,0. Then this represents power -6. And this represents 1.000 with 2. Then it means 1 times 2 to the power of -6, right? Or 1 over 64.
How do you represent 0 in this?
Good question. Right. Good question. So that's the reason why I didn't want to cover the smallest number in this direction. Smallest number that we can represent changes. But in any case, as far as this limitation is imposed, we can represent numbers between 1/64 and 240. So anything above this is called overflow, right? Overflow. And then I will mention about underflow later after covering the normalization. So please browse everything up to this point and ask me if you don't. Then I will calculate a few possible maximum number problems. Any questions? And let's change the design. I don't care about the details. I only care about the maximum number that it can represent. So sign bit doesn't hurt, either on or off, it doesn't matter, right? And then exponent bit, and then fraction bit. Assume that you have 10 bits to represent the exponent, and then 9 bits to represent fractions. Then what is the maximum number that we can represent? That is my question. In binary form, or if you want decimal form. So this is the maximum number that we can represent. So this number is the bitwise conversion of the bits there, right? And then bias is subtracted, right? What is the bias? If you have 10 bits, bias is 2 to the power of 10 minus 1, 9 minus 1. So bias is subtracted from this bit representation, right? This is the bit representation. If you have all ones, then it is 2 to the power of 10 minus 1, right? All ones is 2 to the power of 10 minus, but you have 0, so 2 to the power of 10 minus 2. If you don't follow me, ask me.
Why is it 2 to the 10 minus 2 instead of minus 1?
If you have 1, 1, 1, 1 everywhere, then it is not bigger than 1, 0, 0 in 11th bit, assuming that we have 11th bit, right? So 1, 0, 0 in the 11th bit is 2 to the power of 10. So that is 2 less than 1, 0, 0, right? So I will show you the reason. It is binary representation of a number. So we have right? We have 11-digit number. Then this number is 2 to the power of 10. Do you follow me or not? Assume that you have 1, 0 in binary representation. In decimal representation, it's 2 to the power of 1, right? If you have 1, 0, it's 2 to the power of 1. So we have 1, 0 here, it is power 1. If you have 2 zeros here, then we have power 2. Assume that you have 10 zeros here, then it's 2 to the power of what? 10. If you don't follow, ask me. That's the reason why the first item that I covered on the web, it was this number conversion, right? This number representation. This number representation. So when you have zero zeros, when you have 1 0, then it is power 1. When you have 2 zeros, it is power 2. When you have 3 zeros, then you have power 3. When you have 10 zeros, then it is power 10. If you don't understand, ask me. If you do, then I will continue. Then 1 less than this number is what? 1 less than this number is right? 1 less than this number, right? If you don't understand, ask me. This number is 1 less than the previous number. Two less than this number is the one that I gave you, right? 2 less than this number is the one that I gave you. That's the reason why we converted this number and then subtracted bias to calculate the exponent. And this number is straightforward. So this is the maximum number that we can represent. Because it is 3 o'clock, let's take a break until, by this clock, until 3:10. So let's resume at 3:10, and you may ask questions at that time. So I will correct this problem. And because of this reason, it should become -1. Calculation of mistake. So it should be, so 5/11 power is the correct one. If you have a question up to this point, ask me. If you don't, then I will show you how large this design can represent, right? This design, 1 bit for sign, 10 bits per exponent, and 9, total 20-bit number, right? This 20-bit number can represent this number, right? And this number is almost 2. This number is almost 2. So in this sense, it's 2 to the power of 5, 1, 2. So I calculate this using maple, then 512 is this one. Then it's roughly this large number, right? Can you recognize this number? It's very large, right? How many zeros are there? Almost, it is a 155 digit number, right? 155 digit number. That is very big. All the money in the world cannot be as much as this. Only about everything up to this point might be all the dollars in America, right? Maybe about somewhere around here might be all the dollars in America. Or particles may not, I don't know, or particles on Earth might be somewhere. So it's really large. If I just use zeros, it has 154 zeros. So in this design, with just 10 bits, we can represent this big. We can represent this big. But if you have any question up to, I wrote, even this should be correct. I made a mistake in this calculation. It should be 11. I made this mistake. So any question, if you have any questions, ask me. If you don't, then I will mention about IEEE design. How IEEE assign bits. How many bits are assigned for fraction? How many bits are assigned for exponent? So this is it. IEEE follow this scheme with this design. Exponent bit is 8, and fraction bit is 23, and then sign bit is 1, and then total number of bits used here is 32-bit number. So if we say 32-bit floating point number or real number, then it is this. And if it is 1 sign bit and then 11 exponent bits and then 52 fraction bits, then it becomes 64-bit number. So this is called usually double precision number, right? Single precision real number, double precision real number. So I completely covered everything up to this point when it is normal. When it is normalized, we covered. And once you completely understand everything up to this point, I will begin to mention about the normalized case and not a number or infinity case. Then, if we're going any further, I will use real representation of double precision or single precision number. So single precision representation of this thing should be what? So you should answer. So I will group it first to make it easier. So assume that you program something, and then once you check bit representation and you found this number in the debugger or something, then you should convert this number to a real number that you can understand. So please convert this number to a number. So what number did you get? Excuse me? -6. So let's check whether this is correct or not. So sign bit is 1, representing negative, right? Exponent bit is 100, meaning, right? 10001 means 2. And fraction bit means 1 point and then these things 1 1,
That's -7.
and then this becomes 1 plus 2 to the power of -1 plus 2 to the power of -2, then 4 plus 2 plus 1 upstairs, and then 7 over 2 to the power of 2. And let's represent the number. -1.11 multiplied by 2 to the power of 2 becomes -7 over 2 to the power of 2 multiplied by 2 to the power of 2, -7. So 1 off, right? You forgot 1 off.
Yeah, I dropped one.
So this number represents -7. If you didn't get it, or if you have difficulties, ask me. So it is -7. -7. Then let's do the double precision number. So double precision number uses 11 bits to represent the exponent. So it looks like 1 0 0 0 0 0 0 0 0 1 0. So this is the exponent, and then fraction part 1 1 1 0 1 0 0. So find this number. Please check what this number is, and if you find it, you can let me know. So what is the number that you found? So negative 13 is the first answer. So let's find it. Sign bit is 1, so it means negative. And exponent bit means, after removing it, 2 plus 1, 3. And fraction bit is 1, and then use these numbers, right? 1, 0, 1 with binary representation. Then it is 1 plus 2 to the power of negative 1 plus 2 to the power of negative 3 multiplied by 2 to the power of 3 with negative sign. So this is it. Binary representation is done. Then let's convert it to decimal representation. Then we can multiply 2 to the power of 3 inside, then 2 to the power of 3, 2 to the power of 2 plus 1, and then it is a plus 4 plus 1 and negative 13, correct. Any questions? Then I will check these things in the debugger, and I will show you how these are designed. So negative 7, and I want to store negative 7 in single precision and negative 13 in double precision, right? I want to store negative 7 in single precision, negative 13 in double precision. And I will create my C program using negative 7 in A and then negative 13 in B, and then single precision and double precision, and I will compile it, and then I will run it. When I run it, I can open the debugger and then find the stuffs. And you can look at this memory location, and this is the position to store A, right? And the next one will be stored here. So let's go ahead. So you can check the change, any change appearing here when I step over. So please look at it. It is CCCC, right? So I step over, then it changed to, I will copy it. Did you see it? What was it? I will show it one more time. 00 E0 C0, right? 0, 0, E, right? 0 is a little endian, right? So it is 0, 0, E, 0, C, 0. So I wrote down the result in little endian form. And then negative 13 will be stored in the memory, computer memory. So I will step over this line, right? I step over this line, then this will change these 4 numbers, right? These 4 numbers will be changed. Oh, double precision. So for A number search, it uses this 64 bits, right? 32-bit plus the previous number is 64-bit. So those A numbers were changed. So I will write this result in little endian, and up to these things are zeros, right? So I will use zeros. So total 6 zeros, and then E2AC0, right? 2AC0. So I stored A equal to negative 7, right? I stored minus 7 in A location, and then I showed you the change of the memory, and then let's do the conversion of this hexadecimal to binary. Hexadecimal to binary is very convenient conversion because 2 divides 16, right? Because 2 divides 16 is very convenient conversion. So let's do it. If we convert it, then 0 is, so usually one number occupies 4 slots. One number occupies 4 slots. And then this number occupies 4 slots. And this number occupies 4 slots. And this number occupies 4 slots. And then E is written how? It is what? E is A is 10, B is 11. So I will represent bit. I will use bits. So A is 10. 10 means 1, 0, 1, 0. B is 1, 0, 1, 1. C is 1, 0, 1, 1, 0, 0. Do you follow me? 1, 1, 0, 0. D is 1, 1, 0, 1. E is 1, 1, 1, 0. So this is 1, 1, 1, 0. And then 0, 0, 0. And then this C is 1, 1, 0, 0. And then 0, 0, 0, 0. This is it. This is a bit representation in the memory, right? So when you program, you say A is equal to something, B is equal to something. Then it goes to memory. When it goes to memory, it occupies total how many bits? 32 bits or 64 bits. Then let's write it. 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, and then all zeros, right? So let's break this up. How many sign bits? 1 sign bit, right? How many exponent bits? 8 exponent bits. What about the fraction bits, remainder? So check it. Did you get this result or not? Let's go up to the problem. Let's go up to the problem. Exactly the same, right? Exactly the same. 1, 8 bits, and then 1. I derived exactly the same thing, and I show you the memory. So whenever your program has some problem, you can go to the debugger and go to the memory and check the number. You see a lot of strange names like this. You see strange things like these, right? You see strange things like this. Then what does this mean? this means a number, floating point number, then you can convert it. And you can check, oh, I expected, for instance, 5 to be stored. But instead of 5, 7 is stored. So in other words, the portion changing 5 has some problem. So you can debug. So please convert this problem, the same A, in bits, to practice 16-bit representation, not 16-bit, hexadecimal representation to binary representation. So please convert these things to 1 and zeros. You don't have to convert these 6 numbers, but convert top 2 numbers. So let's check whether our conversion is correct or not. So take a look. 1 and then 11 digits, right? 11 digits. So I will break this up. 1 digit and then 11 digits. Right? This is total 11 digits. And then fraction digit. And then do we have a match? We have an exact match, right? So I showed you how to do it. In fact, about 8 years ago, when I submitted about 120 files of ProE program, ProE suddenly behaves strangely. But it cannot be found in the debugged version. In other words, the only way to find the error is going to the memory. Only by watching this memory, we must track down the error. So by just watching these things, we should track down the error. So when you do these things, we should convert all the numbers and check what is going on. So these things are very, very essential in understanding, especially in debugging these stuffs. So roughly, I showed you what happens inside a computer following IEEE standard. When you say A is equal to -7, when you say B is equal to -13, the computer stores it this way. And if you want to check other things such as plus or minus signed integer or non-signed integer, we will see the same patterns. But you should be careful because this is little endian, so you should locate it in the earliest memory, right? Smallest memory, and then locate the second one and second one and so on. So I covered the normalized case. And if you have any question about the normalized case, ask me. If you don't, then I will begin to mention about the normalized case and infinity case.
How do you know where to look in the debugger?
Oh, I see. In C language, there is a command. When A is stored, then the memory, the address of A can be called this way, address of A. Then it represents the memory location, and I typed this memory location here, and then go there. If you want to test it, I can show you, but it's not debugging course, so let's not do that. Just I wanted to show you the bit representation of numbers. So you now have confidence in this normalized case. So the only remaining two cases are all on or all off. In other words, 0, 0, 0 in exponent is all on or all off. 0, 0, 0, 0 case, or all on, 1, 1, 1, 1 case. Anything in between is done, right? Anything in between is done. So I will handle this first because it's easier. This represent infinity or not a number. Then when is it infinity and when it is not a number? Simple. Exponent should be this, and all the entries should be, I will look at the design, and I saw it. And all the fraction part, right? Fraction parts are zeros, right? All the fraction parts, these are zeros, then infinity. Otherwise, it's not a number. And not a number can be very many different not a number exist, but in this course we don't want to care about silent or quiet or something, right? So just not a number. So take a look. Assume that we have design like this. Oh, sign bit can be anything, right? And then exponent bit is R1. And then fraction bit is this. Then what does this mean? This means what? Infinity. Right? But assume that somewhere we have 1, right? Somewhere we have 1. Then what is it? Not a number. So in this sense, infinity or not a number is trivial. Any questions? And finally, exponent is 0, 0, 0, 0. Case will be mentioned, unless you have questions about infinity or not a number. It's called the denormalized case. Denormalized case is still a number. It's still a number. We could represent numbers using exponents in between, right? We could represent a number using exponents in between. Right? All these things represent a number. And in fact, even this one represents a number. But this part is normalized part. This is the normalized part. And what is your guess? Normalized and denormalized means only one difference. What do you think is the difference? We skipped first starting fraction number in normalized case, right? So we skipped it. We skipped it. So this is the normalized, right? Right? But denormalized case is this. Oh, what about just 0.00000 something? So it's 0, it should be 0, and then 000 something. So this thing. Then it's not normalized anymore. We do not assume anything in front. We do not assume anything in front. Right? We just convert this as if we are converting binary number to other numbers, right? To decimal number or other numbers, right? We just read it as a number. So in other words, 1 point something is not assumed anymore. We represent it this way, 0 point something something here, and then we write these numbers without assuming 1 here. It's like this. So it means this. Because exponent is fixed, right? This representation is fixed. I fixed the exponent too. Do you follow me or not? Because exponent is fixed, I fixed the exponent too. Right? Because 0, 0 is fixed. We cannot have pairing numbers, right? Just a 0, 0. So for that, what exponent do we assign? We assign 1 minus bias, right? We assign 1 minus bias. In other words, the exponent is fixed. After fixing the exponent, we may have some fraction part, right? We may have some fraction part. That kind of fraction part can be written. So I will use the normalized case. Assume that you have this thing. So let's return back our 8-bit number case. 8-bit number case, then 0, 4 bits per exponent and 3 bits per number. So 8-bit number case, then 0, 0, 0, 0. Right? Exponent is this way. And then this number can be 0, 1, 1, or 0, 0, 1, anything, right? So assume that this representation is given. Then what does this mean? This means plus sign, and then 2 to the power of 1 minus bias, right? Bias will be calculated soon. Bias is not difficult to calculate. And then multiplied by 0 point. So like this, like this. Point 0.011, right? 0.0. So we don't even attach 0 here to avoid any confusion, right? So we completely remove everything before this decimal point and before this floating point, and then just. So this is the meaning of this number. So please browse it and ask questions. Then what is this number? What is bias first? In this case, what is bias? Thank you. Bias is always fixed, right? 2 to the power of n minus 1 minus 1, right? 2 to the power of 4 minus 1, 4 minus 1 minus 1, 2 to the power of 3 minus 1, and 7, right? So bias is 7. So 2 to the power of minus 6 multiplied by this thing. This thing is 1 times 2 to the power of negative 2 plus 1 times 2 to the power of negative 3. Right? So if we extract the common denominator, 6 power and 30 power, 9's power, then it is 2 plus 1. So 3 over 2 to the power of 9 is the 1, represented by this denormalized expression. So normalized and denormalized, all numbers. Normalized assumes 1 point something. Denormalized one does not assume anything. Just point, even 0 can appear here. If you don't have a question, I will go to the next page and practice a few more things. So please find this number. What is this number? So what is this number? So do you have this result or not? If you don't, then ask me. So denormalized number. Then let's find the maximum that can be represented using denormalized form, and the minimum that we can represent using this denormalized form. Because this is fixed, right? Other than the sign is absolute value, can remove the sign, so sign is not considered. Then with this fixed exponent, the maximum number that we can represent is this one, right? And the minimum number that we can represent is this one other than 0. Assume that everything is 0. Assume that everything is 0, then we define this to be 0, right? Assume that we have everything equal to 0, then it's 0. It could be plus and minus, right? So it could be on or off, and it could be plus and minus 0, but still 0. So we wasted one representation because plus 0 and minus 0 have different bit pattern, but still the same 0. But except this waste, we don't waste any space. So please check what is the maximum number that we can represent and what is the minimal number that we can represent using this. Then the maximum number is and minimum number is Any questions up to this point? Then let's combine normalized and denormalized. Assume that we want to find the minimum number with normalized exponent, right? So with normalized thing, then it should have 1, right? This is the minimum number that we can represent with normalized form, and the minimum number that we can represent is this one, right? This is the minimum number in normalized form, right? This is denormalized, right? Then this number means 2 to the power of negative 6 multiplied by 1.001 in binary representation, and this means we already calculate the minimal number before. Then take a look. The maximum number that we can represent with denormalized form and the minimum number that we can represent using normalized form, and compare it. What is bigger? Or what is smaller? What is smaller? The denormalized number is smaller than the normalized number, no matter what. The biggest denormalized number cannot be bigger than smallest normalized number. Yes?
I understand how you got 2 to the minus 6 there for 0001.
It is this way, right? This number in binary form is 1, right? And then minus bias, right? And bias is 7. So 1 minus 7 is negative 6. Or if you want the chart, then you can write it. 0, 1, 1, 1 is 0. And then you can go down, 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 then go up to this point, right? Then these points are down, right? That means negative 6. Do you follow me? These difference, right? This means 6. Any other questions?
Why can't the smallest normalized number have all zeros in the fraction part?
Oh, yeah, you're right. You're right. Sorry for the mistake. Sorry for the mistake. So I made a mistake. I somehow thought denormalized non-zero case. Yeah, still, sorry for the mistake. Yeah, I was confused between denormalized and normal. Normalized number, we don't have to worry about 0, right? Anything can fill the position, right? Still, even in this case, the normalized number is smaller than the normalized number. So the normalized portion represent smaller part. Then, as you can see, the smallest number that we can represent is this one, right? Smallest number that we can represent is this one. And what is the biggest number that we can represent using normalized form? N is not a good idea, just number, right? We can represent using AP number. How many numbers can you represent? Especially, what is the maximum number that you can represent? Please calculate the maximum number. Did we calculate the maximum number before?
Yeah.
In normalized form. Do you have the result, or you may calculate one more time? So 240. So with our 8-bit design, right? Our 8-bit design with 1 sign bit, 4 exponent bit, 3 fraction bits, we can represent the numbers between 2 to the power of negative 2 to 240 excluding 0. 0 can be represented by filling every term, every bit with 0, right? So 0 can be represented. But other than 0, the minimal number that we can represent is this one. The maximum number that we can represent is this one. Anything under this between 0 is called underflow. So you may encounter underflow error. Anything above this is called overflow. So either underflow error or overflow error may occur, right? Anything like 2 to the power of negative 20, right? 2 to the power of negative 20 may cause underflow error. Anything bigger than this, like 350, may cause overflow error. So computer checks whether it is inside this boundary. All other numbers inside this boundary can be located somewhere. It may not be exact matching, but at least you can find some position, anything in between. But it's still smoke and mirror. Some different numbers may go to the same bit representation. So I will pause, and then you may ask questions, everything up to this point. If you don't, then I will use a few examples and then calculate maximum and minimum number. Maximum means normalized maximum. Minimum means denormalized minimum. No questions? Then a few examples. that you can check. So 8-bit number will be used, right? So 8-bit number with this design. So you may pick any combination, 0, 1, 0, 1, 0, 1, 0, 1. Or, so this is the first number. Second number is 0, 1, 1, 0, 0, 1, 1, 0. Third number is 1, 1, 0, 0, 1, 0, 0, 1. And then fourth number is 1, 0, 0, 0, 0, 0, 1, 0. And fifth number is 1, 1, 1, 1, 1, 0, 0, 0. And sixth number is 1, 1, 1, 1, 1, 0, 1, 0. So please find all these 6 numbers. And if you can find all these 6 numbers, then you successfully follow everything.
Normalized.
Right. 3 things are denormalized. This is denormalized, and these are other cases. So if you got these things, you completely understand everything. If you have some difficulties, you may ask. So let's check individual problem. First of all, are there non-normalized case, not denormalized, but non-normalized, meaning infinity or denormalized case? This is normalized, right? This is normalized. What about this one? First, denormalized case. And this is infinity or another number case, infinity or another number case. So I classify them. So let's enter denormalized or another number case. Denormalized case has 2 to the power of 1 minus bias. Bias 7. So 1 minus bias is negative 6. Multiplied by this bitwise representation of this number, meaning 0.010, right? It's 0.010, denormalized number. What about this number? 1111, right? All on, and then 0, 0 in the fraction part, so meaning infinity, but we have negative sign, so negative infinity. If you have plus sign, then it's plus infinity. What about this one? You have 1, 1, 1, 1, all on, right? But we have non-zero number here. So it's not a number case, right? It doesn't care whether it's plus or minus, not a number. So, unnormalized cases are covered. Not denormalized, but non-normalized cases are covered. Then let's cover normalized cases. Normalized means attaching 1 in front of this thing, right? Attaching 1 in front of the bit representation. Other than this, straightforward, right? 0 means plus, and then this means after subtracting, after removing this 1 and then adding 1, it is 3, power 3. So plus this multiplied by this number in binary representation, and you can find the decimal representation too. What about this number? It is 1.110. And then after removing this number, this is 4 plus 1, 5. And what about this one? After removing this 1 plus 1, 2. Minus sign. And then 1. So once you look at this, you should know what the real number represented by the bits. Yes?
I'm getting confused with the exponent and the bias, the removing one.
Uh-huh.
Can you run that by me again?
No problem. So you can, so I will look at exponent part, right? Exponent is this bit number, right? Bit converted to just straightforward binary number, right? Minus bias. This is it. This bit representation converted to binary number minus bias if it's normalized. If it's not normalized, or if it is denormalized, for instance 0, 0, we fix the exponent to 1 minus bias. But if it's normalized, this bit binary number minus bias. So denormalized case has the fixed exponent no matter what. But this normalized case, then it may change, right? Then that number can be converted this way. Bias.
Okay, so example then. 1, 0, 1, 0.
So 1, 0, 1, 0 minus bias, right? And we have 4 bits, then bias is what? Bias can be always calculated. Bias is what? Please calculate bias.
n minus 1 minus 1.
So that is 7, right?
Okay, how do I get that?
2 to the n is what? 4 bits, right? Minus 1, minus 1, right?
Okay, so what if that, instead of 1, 0, 1, 0, I got 1, 0, 1.
Oh, I see. We are not caring about this thing yet. We are just calculating bias. Bias. So
Okay, is the number of bits, 2 to the number of bits minus 1.
right, the number of bits is 4, right?
Right, because I have 4 bits there.
Right. So this number is 7.
Got it.
So bias should be calculated no matter what.
Right.
Then simple. You convert this to a number minus bias. That means this number from binary number minus bias is the number.
That's what I'm getting. Okay, so what is 1, 0, 1, 0? What is that number?
1, 0, 1, 0 is what? 1 times 2 to the power of 3, 0 times 2 to the power of 2, and then 1 times 2 to the power of 1, plus 0 times 2 to the power of 0, minus bias. Then you can calculate it, 8 and 2, 10 minus 7, 3. Then I will summarize these things by running a program, and then let's input all possible cases. After you write down these things, I will really show you what happens in a computer algorithm or memory. So let's do it. So I will run it, and then I will change the program, unsigned integer like x equals what? Like 7, right? Unsigned integer x. And then signed integer y equals 13 or 15. So I want to check what happens to x, y, a, b, or the case that we covered, right? Unsigned integer, float, double. Float means single precision number, double means double precision number, integer, unsigned integer. So all these cases will be shown very soon, unless you have a question. So I compile it and run it. I will set the breakpoint here. So I will run it. And then let's check what happens inside. First of all, I want to check the address of x. Address of x is given in hexadecimal. So I will write the address here. 12FF7C. So this is the address, right? This is address. So this is address. Then let's step over and please focus on this thing and check what happens. What did I do? Sorry. So take a look. This happened, right? This happened. It's little endian. This is little endian. So let's do it. So I will write this result. So I want to get x is equal to 7 was the one that I wrote, right? X is equal to 7, right? And the memory has this thing. So it is written in little endian, 0, 0, 0, 0, 0, 0, and then finally 0, 7. Little endian, right? Any questions? So let's write it. If we write it, then it is 7 is 1, 1, 1, 0, right? And then 0, 0, 0. So let's run the next thing. Then run the next thing. Then what happens? If we run, then y will be found. So this is what he can get, right? This is what he can get. Oh, I should have used negative 15 because it's signed. I don't. So 15 is obvious, right? 15 is F, right? 15 is F. It's obvious. So let's not worry about this thing. Finally, next thing is. We already did this thing, so I just show you the change, right? So we just ran it. Then I will change the program to negative. We wanted to see signed case, right? So compile it and run it. And then look at the change in the memory. If you run it, then x changes, right? X is stored. 7 is stored, right? And then 15 will be stored. But now 15 is not f anymore. Do you follow me? 15 will not be f anymore. It will be converted to invert and add 1 stop, right? So suddenly it takes this one, right? So FF in little endian, right? And then F1, right? This is the one that we can write in little endian, right? In little endian it's written, but I wrote it in easier form that we can recognize. Then what happens? Convert these things. Then F is converted to 1, 1, 1, 1, right? F is converted to 1, 1, 1, 1. F is converted to 1, 1, 1, 1. And F is converted to 1, 1, 1, 1. And F is converted to 1, 1, 1, 1. And this is converted to 1, 1, 1, 1. And F is converted to 1, 1, 1, 1. This is converted to 0, 0, 0, 1. So I completely converted it. Then let's really check what happens to our bits. So usually 15 is equal to, in bit representation, 15 is equal to 1, 1, 1, 1, and then all zeros. Do you follow me? This is 15 in bit representation. So we invert these things, right? We invert these things. Then it becomes 1 everywhere up to this point, and then 0, 0, 0, 0. Invert and add 1, right? Invert and add 1. So take a look. Take a look. Exactly this happened, right? So I completely covered IEEE number representation. And once you need to check the memory to find your numbers, you write the bit representation and then convert it accordingly. If it is signed integer, then you should use this scheme. If it is unsigned integer, then just straightforward conversion. If it is floating number with single precision, then you use the appropriate number of exponent and double precision, the stuff. So I covered completely. And if you have a question, ask me. If you don't, then I will answer. Oh, we should finish. Any questions? Then let's stop here.